category of just additional notes is what we call functional group transformations. Now, what do we mean by functional group transformations? Just like take one functional group, right, exchange it with another. When do we need it the most? Think about SN1, SN2 reactions. Like the first thing you do is what? Yeah, you look at the leaving group. It's a bad leaving group, make it into good leaving group. And really the one that is covered a lot in the book is H+. And you use that with alcohols. Because then the leaving group becomes water, and water is a reasonably good leaving group. Okay. Turns out there's a bunch of other reagents, and I just wanted to show you some of these other ones. One of them is thionyl chloride. And the structure of thionyl chloride is this. You have a sulfur in the middle, double bonded to oxygen, and then single bonded on each side to two chlorines. And the thing about this sulfur is that you can attack this with a nucleophile. It's got 3 other electronegative groups on it, and you've got a good leaving group on it. Okay. What's going to happen in this reaction with thionyl chloride for the transformation of alcohols is you'll take an alcohol like this, and you'll add thionyl chloride to it. So this is like one of my favorite reactions. So I'm just going to warn you, because it's probably the first time I've really said a lot of this. That means you should memorize the mechanism. Because it might be handy on the next test. Okay? And you might want to memorize like why I like this reaction, because it's a general principle that is used in chemistry that makes it really valuable. It's a whole class of reactions that we allow this kind of thing to go on. So what does that mean when I say that, by the way? Could know it because it could be on the test. Right? So whenever I say, oh, that's my favorite reaction, man, you should really know that. Right? These are not subtle hints of, yes, you should know this, it's a good idea. It's just like, you better know this or you're going to feel really bad later. Okay. So this is the mechanism. Oxygen comes and hits the sulfur. Now sulfur can actually hold more than 4 bonds, but typically what we do is then we draw this next. So we have oxygen coming in, we have a chlorine coming off as a leaving group. It's just a nucleophile, electrophile mechanistic step. And then what do you get out of that? What left? Chlorine, so it'll be a chloride, right? I just thought I'd do that one first and get it out of the way. And then the other one's going to be this. And a positive charge on the oxygen. And that, again, that balances the charges out. So I have the chloride ion plus the alcohol now attached to what was thionyl chloride. Now, as far as writing mechanisms go, I don't care if you do what I'm going to do next or if you just continue on. Like in a lot of times what organic chemists will do, we'll just add the next thing here, draw another arrow, and just keep going on and on and on. It doesn't matter if you go from left to right, down and back, and down and back and zigzag, or you go like this and back and this and back. It doesn't really matter. Your book, when you see it in the answer key, right, that's just for space. You could write out every single line one at a time. So what I'm going to do initially is I'm just going to write out every single line one at a time. But just know that if you want to condense it because you're tired of writing the same thing over and over again, condense it a little bit, okay? But I know these are all things that people find confusing in organic chemistry. I mean, not like there isn't a shortage of things in organic chemistry that can be confusing. So I'll end up with this. I'm just going to rewrite what I had. Of course, it takes longer to do this. Eventually, I'll just start condensing it all. Now, at this point, I need to introduce my friend and yours. And who says your friends can't smell? Sorry. This is pyridine. And I haven't used pyridine in years, but it's just a benzene ring with a nitrogen substituting one of the carbons. Kind of, if I remember correctly, it smells like, not good fish, but like dead fish. Right. So that's why your friends can smell, because pyridine will be your friend. What we like about pyridine is its acid-base properties. Now, is that an acid or a base? Base, because nitrogen has a pair of electrons on it. Okay? And what we really like about pyridine, if we can get away with using it, is that pyridine is a great base. Okay? Not a good nucleophile. Yeah, it's like a football player. Little tiny head, big giant shoulders. Doesn't fit in a lot of places. So I say this, my son's a football player. He doesn't quite look like that, but I think it's just because my family has giant heads. Okay, so what the pyridine does is acts as the base in this reaction. Now, pyridine in this reaction is usually the solvent. Okay, so on this first, well, I'll write the overall reaction in just a second. So this pair of electrons is going to come and grab that hydrogen and kick these electrons off. So its only purpose is to remove that hydrogen. Well, amongst like dissolving everything and all that other good stuff. So then what you end up with is this. And then the important step happens. Turns out this stuff that's down here makes a really good leaving group. So now the chlorine that you released up here can act as a nucleophile and kick this thing off. Okay? That is, the chlorine comes back into the picture. So I'm going to show you what I mean by sometimes we just write it. Kind of write it and just continue on with what we have. Okay? This pair of electrons comes in from here and attacks. And then this group leaves. Now, I'm going to do something I know, according to your book, we don't do, but I'm just going to tell you. I'm going to do that. That's typically how that arrow is drawn. Because what your book says you never draw an arrow to a bond. But what's going to happen here is this pair of electrons is going to form a double bond between the sulfur and the oxygen. Okay? Now, if you want to draw that one to the sulfur, I'll let you do that. I'm just saying that's just the way we normally do it. And then this is going to leave. You can also draw it in two steps where the questionable bond does this, and then you form, instead of what I just showed you, you form this. Where then in the next step, you're going to go like that. Okay? And that ends up being the same thing. So what did we just make? And this part I like. It's an SN2 reaction, right? So I'm going to draw my product. This pair of electrons comes in, this kicks off. So when I draw my product, which direction is the chlorine pointing? You know, so I put stereo through this whole thing, I put stereochemistry. It's in the back, okay? Plus, what's that?
I said backside attack.
Yeah, a little early for that. Like at 1 in the afternoon, that's great. I haven't had a cup of coffee yet. So, what else is there though? SO2. And chloride again. Good leaving group. What do we know about SO2? Like, think all the way back. Don't think OChem. Think like 3A or 1A. What state? High school. What's if you could? Did they go to high school? What state is SO2 in? Huh? Solid, liquid, or gas? No, just state. I mean, yeah, like simple things. You're getting all too. It's gas, right? Okay, and if you didn't remember that, it's okay.
That's a while ago.
Yeah, isn't it? It's like back when like solid, liquid, and gas was like a difficult concept. Like it's solid, it's liquid, it's gas. Okay, so the reason this is good is because the SO2 does what? It goes out of the solution. Okay, so now SO2 leaves. What does Le Chatelier's principle says happens to this reaction? Shifts to the right. So the reason I like this reaction is because, one, it's a very efficient reaction. It produces SO2 gas, which by itself leaves the solution and helps to drive the reaction to the product side. So it's a very efficient reaction for that purpose. Okay. So why would you want to do this? Okay, let me show you why you might want to do this. Let's say you wanted to make there's a saying that all organic syntheses start with alcohol. Maybe it's a little too early for that saying, but yeah, it's true. The reason is alcohols are very readily available. We can make alcohols like nobody else's business, so these are cheap. And a lot of times we take alcohols and we make other things out of them, and that's why we deal so much with alcohols in organic chemistry. Of course, I think the person who made up the saying was thinking about a different alcohol, but that's just a whole different. Okay, so anyways, I wanted to get that out there. Oh, am I not? Oh yeah. So here, let's say I want to do that and make that, but with this stereochemistry. Okay, so that's what I want to make. How do I make it from the alcohol that's given? So let me go back and we're going to outline this synthesis. Oh, Mr. Horton, since you're here, do you have your little?
Actually, I don't.
Oh my goodness! I didn't steal it. Trust me. That's what I want him to think. Gave it to my wife. Actually, that's what I did with mine. I gave her mine, and I was thinking, oh, he'll be here, and I'll just use his. No, that's okay. I don't know what I did with all the other ones that I've had in my life. Yeah. Okay, so this is what we're trying to do. And so I'm going to teach you one of the, and Dong pointed this out actually in lab the other day, and I thought, you know, and It is. It's just one of those things that you learn how to do. I want to make that. Okay. So another general principle of organic synthesis, okay? You could put Na next to anything and make it a nucleophile. So like if you look at that, you say, okay, the OH has to leave. And what else? I have to add that OC double bond to OCH3. I have to add an acetate group, right? So then your nucleophile, the thing that you're going to add, and details might vary. You might just add this. Now there are limitations to this. Just add that. That's your nucleophile. Because that's what's added on and replacing the OH. So you don't have to think really hard. Like if you see something there, like if it was this, what are you adding? All right, draw a line here. You're adding CN, right? So what are you going to write? NaCN. And it seems absurdly simple, but that's all you have to do at first. You're going to have to learn, like you can't do some things later, but for now, I think this is a pretty good piece of advice. You can thank Dong for later by buying him a Coke or something. He works really cheap, let me tell you. Okay, so now what we want to do is we want to take this 2-butanol and produce this acetate out of it, okay? So what's the first step that's going to happen? First step, thionyl chloride. Yeah, I'm going to draw an arrow like this. And I'm not going to draw the mechanism because I already just drew this one. SOCl2. It's in pyridine. I'm just going to stop right there because I don't want to run over the molecule. Then SOCl2 with pyridine would give me this. Okay. Get an inversion, right? And then, next step, just add this. Now, however you want to write acetate. So, but typically we'll just say CH3COO minus and then Na plus with it. Now, sometimes sodium's not used. Sometimes we'll use potassium or ammonium ion. It just but that's a detail that if you actually did it and you try to dissolve it and it stayed solid in solution, you go, well, that one didn't work, and you try different ion. Right? It's not rocket science in a lot of ways. Okay. So far, so good, right? Now, let me ask you this, though. By the way, it was Brittany that pointed out that, that stuff's not in the book very well.
No.
I mean, it's there a little bit, but what if you want to do this? They don't go over the mechanisms of the reagents as much or why you would want to do it as much. So let's say you wanted to do this. So that produces a whole nother conundrum. Oops, that's not what I wanted. And the reason this might be hard is perhaps a little more subtle. But what do you think you add? Yeah, you would try to add Na, the CH3OONA, right? Sodium acetate. Problem. Acetic acid pK is 4.7. Hydroxide pKa, you may know, it's about 15 for water, H2O, right? Not going to happen. Like if you try to put this as a much weaker base than that is, that's never going to leave in the presence of this. So that's a general problem. The other problem is, what's our normal strategy for getting rid of this? Acid catalyst, right? So acid catalyst here, produce this would then be acetic acid, all right? Polar protic, all right? What kind of mechanism does it favor? SN1. What happens to your stereochemistry in SN1? It becomes racemic, right? You get a mixture, so you can't do that. That's one of the reasons, these other techniques are important. Is it avoids the racemization of the chiral carbon. Now, if you didn't care about that, then yeah, go ahead. Right? It might work pretty well. And you would reflux it in acetic acid, and at the end you would end up with racemic acetate. Okay? So the reagent that they use, we talked about these as leaving groups, is tosyl groups. So to give you an idea, here's one. Am I drawing this too small? Well, you guys familiar with the circle that just replaces the 3 double bonds? We'll use this. A lot of times this is just abbreviated TSCL or PTSCL because this is para. That refers to this orientation of this methyl group on the benzene ring, but it doesn't matter. It's known as a tosyl chloride. This is a tosyl group, and this is the chloride. Okay. What's the chloride? Good leaving group, right? So same principles apply to this reaction. So what you do is you can take the starting material like this, and then put in tosyl chloride. So let me, I'm going to draw a generic. The R just represents a bunch of different things that I could put there. What's the nucleophile on the alcohol? The O of the OH, right? So this is going to attack, and the chlorine's going to leave. Let's put a pair of electrons in there. Oops. Try my arrow again. And then I end up with this. However you want to draw the rest of that, but I'll just draw it like that because it looks prettier to me. Okay? And then what happens?
It leaves.
It's close. You need a base. Pyridine could be the base. It could be other things. Okay? So I'm just going to call it B. If you use pyridine as your solvent, or you use other aprotic solvents because you don't want to promote SN1 reactions. You don't want the leaving group just to leave. You want to control this, right? So now what you end up is this.
Dr. K, how are you controlling what the leaving group like leaving? What did you say there?
Oh, it's just in an aprotic solvent. So it doesn't stabilize a carbocation. It helps to minimize it. You don't heat it. You avoid doing things that might break a bond, that kind of stuff.
Now, is there any specific situation where tosyl has to be used as opposed to just having anything else to protonate or to convert it to a water and get it to a leaving group? Let me rephrase that.
Just when you want to retain stereochemistry.
When you want to retain stereochemistry.
When you want to control stereochemistry, I won't say retain, but you want to control the stereochemistry. That's what you're going to do. You're going to use tosyl, or you're going to use the thionyl chloride. And then I'll list, there's a couple other reagents that we use that are all listed on here. Show you kind of how they work. Okay? But these are all when you're worried about stereochemistry. So in part of the test, Hey, there's your cup. I even washed it for you. Because I didn't want to see it today and have it be all gnarly from last week. You guys put sugar in your drinks and stuff, yeah. But anyways, when you want to control stereochemistry, you generally try to avoid like just straight HCl on a secondary carbon because it will possibly go through like an SN1 mechanism because you'll form a carbocation, HCl, and a protic solvent. So you try to avoid those things when you're controlling stereochemistry. So on a test, when I gave you a reaction that has a specific stereochemistry and a product that has a specific stereochemistry, and I asked for the series of reagents that you need to think about, oh yeah, Thionyl Chloride or Thionyl Chloride. So we're going to compare the products of these two reactions in just a second and talk about why they're different. Okay, so I got that to go. I got this base to leave. I have that, right? So then the next thing, the last step, is to take, and by the way, that's how they usually abbreviate that, just OTS, and you can stop drawing it. You have to draw it in these steps because there's stuff that goes on in it, but then after that, yeah, you can just stop drawing it. And this is when I can bring my nucleophile in. You may have done a workup in between and cleaned up the product and isolated it, put it all by itself, and then bring in the nucleophile. But what's my nucleophile? No? No. I'm trying to go from here to here. And the reason chlorine doesn't... what's that? Yeah, so the acetate. So Na, right? Let's put an A and Na on it. So CH3... COONA. And then you'll end up with, oh wait, this. Just running out of space here. That's the product that we wanted to get in the first place. Okay. So notice what happened. And this is an important difference between these two reactions. In the thionyl chloride, I took the oxygen and replaced it with a chlorine. Right? At that point, I get an inversion of the stereochemistry. And then when the nucleophile comes in, I get another inversion, and so I have a retention of configuration when I go through those two steps. Okay? So the oxygen got replaced, right? Because something nucleophile came in and kicked it off, right? Now, here, the oxygen eventually gets replaced, but in this first step, the oxygen's the nucleophile, right? And then this becomes the leaving group. And so in that process of the oxygen becoming the leaving group, it doesn't change its stereochemistry. It retains its configuration. So when a nucleophile comes in, the stereochemistry is inverted. Okay? Okay. So retention, thionyl chloride, nucleophile. Inversion, Thionyl chloride, and a nucleophile. And you get an inverted stereochemistry. Okay? Any questions on that? A couple other reagents worth mentioning. Oops, I don't want to make it that big. PBr3. Okay, you'll notice in that same, all of these in the bottom list, right, follow an inversion of stereochemistry following to produce the leaving group. Yeah, you can get it. Want one? So PBr3, PI3, that's just not shown there, but I'll talk about it in a second. PCl3 all act the same way. Okay. You'll notice though, like PCl3 or PB R3. PCl3 you buy. PBr3 you can produce in situ. That just means right in the solution when you need it. Okay. You add P plus Br2. And it reforms as PBr3. It's pain to do because what you have to do is keep it below 0 degrees Celsius. You put the phosphorus in, red phosphorus, which is the stuff that you make match heads out of. Yeah, I thought we had some, and it turns out we got rid of it all because it's too dangerous. And we had white phosphorus. White phosphorus, you take it, you throw it in the air, and it goes whoosh.
Awesome.
Too dangerous. Can't keep it in our stockroom, so we got rid of it. I know. I could have got rid of it. All kinds of ways to get rid of that.
That's it.
Yeah.
4th of July.
Yeah, but what you have to do? Oh, yeah, it's
Right now.
right now. What you have to do though is you have to do this really slow, in situ, and then you produce PBr3. Okay, so this makes PBr3. That
say P though? Or is that supposed to be an R?
no, that's an R that's really fat because I'm writing with my finger.
Ah,
Yeah.
okay.
If Chris hadn't forgotten his stylus, it would be a lot more.
Yeah, it's right.
Yeah. Okay, so another one though, you notice I listed phosphorus and I2 in that same list, like. Presumption is that does the same thing. Okay. So how do these work? Just to give you a really quick overview. So I'm going to do PCl3 because that's the first one on the list. What does it have on it?
Electron.
Yeah, it has a pair of electrons. It's got electronegative groups, right? Chlorine's the leaving group. The phosphorus is the electrophile. So again, just like in thionyl chloride, and this again is one of the reasons why I like you to memorize mechanisms, the pattern just repeats over and over and over again. So in thionyl chloride, there's your lone pair, boom, like that. One of these leaves. Okay? So then what you end up with is you end up with R attached to an O, attached to a phosphorus with 2 chlorines on it. Again, you do this in pyridine, so what's the next thing that happens? Get rid of that H, right? You notice how this is like exactly like thionyl chloride up to this point. So then you end up with this. Okay, let's make it interesting. Give it a stereochemistry, even though R, whatever R is. I'm sure there's an organic chemistry god somewhere yelling at me, but that's fine. Nucleophile, Cl. Oops. Can't throw my airhead. Turns out this is a good leaving group. Okay? Oxygen, you know how you talk about what makes a strong acid? Well, you have to have an electron withdrawing group. It's got 2 chlorines on it. It can delocalize by forming a double bond with the phosphorus. There's all kinds of things that it can do. So this, what we've done essentially is created a good leaving group. That would be the same purpose of the thionyl chloride. Nucleophile comes in and kicks off the leaving group. Now, it doesn't decompose and make fire or light or gas or anything like that, but it's still a good leaving group. Right?
Not that great.
Yeah, I know. Yeah, it's all right.
It doesn't give a shit.
Yeah, so if you look, there's a bunch of things listed there. You need to know those. Okay. So, for example, what will I do on a test? And I'm going to put this down to